High schoolers who are especially interested in mathematics and science are encouraged to apply to spend their summer at UC Santa Cruz at the California State Summer School for Mathematics and Science. The Cosmos Summer School gives students who are talented in the sciences the opportunity to explore cutting-edge research and learn what college life is all about. Cosmos is organized by the UC Santa Cruz Educational Partnership Center as part of a larger outreach effort to improve access to college. The 4-week Cosmos program in June and July is for gifted math and science students from 8th grade through seniors. 10 courses are offered at Cosmos, with topics ranging from environmental biology and toxicology to aspects of applied computing. Cosmos is also offered at the UC Davis and Irvine campuses. Cosmos encourages interested students, parents, and teachers to call 831-460-3077 for information, or to visit the Cosmos website at http://epc.ucsc.edu/cosmos/.
Welcome to the second Cosmos Discovery Lecture. I'd like to welcome all of you, those of you who couldn't make it to the first lecture, to this very exciting session. But before I introduce the speakers, I'd like to say a little bit about the astronomy program at UC Santa Cruz. The program started at about the time the university started, in the late 19th century. In 1888, a Mr. James Lick donated the so-called Lick Observatory to the University of California. This is a major set of telescopes situated high atop Mount Hamilton, clearly visible from many areas of the Santa Clara and even San Mateo counties. This observatory is managed, as I say, by the University of California, and the astronomers who worked on top of Mount Hamilton actually lived up there until the mid-1960s, when this campus, UC Santa Cruz, was established. They moved then down from the mountain to UC Santa Cruz and helped establish the astronomy department here at UCSC. Now, the observatory, being managed by UC Santa Cruz, is also part of the larger University of California observatories, which consist, among other things, of the two 10-meter telescopes in high atop Mount Mauna Kea in Hawaii. So with these extraordinary tools, the astronomy department here at UC Santa Cruz is one of the very finest, if not the finest, astronomy department in the country. The astronomers here do research on the physics of planets, both planets here circulating around our own sun and planets circulating around stars in our nearby neighborhood. They study stars, they study galaxies, clusters of galaxies, clusters of galaxies, and the universe as a whole. And so it is with great pleasure that I introduce to you two of the great astronomers here at UC Santa Cruz, Professor Raja Guha Thakurta and Professor Sandra Faber, who are going to tell you about some of the questions and some of the answers to the questions that humans have been asking since the earliest of recorded times. So with that, I introduce our two speakers.
Thanks very much, George. Can you all hear me? I'm Sandra Faber. Not too many people confuse Sandra with Raja, so I didn't even need to explain that. I am Sandra Faber, and as George has explained, we're going to tell you a bit about our work in astronomy here at Lick, and we're going to end our talk with a lot of work being done by Raja. Let me say right now, though, that we have been told that you are all exceedingly bright and exceedingly eager, and that you like to pepper speakers with questions. And so we hope that this morning you'll do exactly that, and that we'll hear a lot from you and have a nice interaction with you during our talk. Now, Raja This is an interesting title that you've picked for this talk, The Birth and Evolution of Galaxies, Time Machines, Cannibalism, and Chemical Pollution. That's a little jazzy. That's jazzier than I'm accustomed to. Now, why did you pick this title?
Well, we'll get into the details of the title in a minute. I guess galaxies are very important entities in the universe, and I thought I'd ask you what you thought, why you thought galaxies, why we even care about galaxies. There are all kinds of things in the universe. Why galaxies?
Well, you know, I might not have thought of galaxies first. If you had asked me about fundamental entities in the universe, I don't know, I might have said atoms.
Or what kind of atoms?
Oh, I like carbon atoms because I have a lot of them.
But, you know, carbon atoms weren't around when the sun was formed.
Really?
Carbon atoms were produced in the sun, right? So the sun had to have come before these carbon atoms.
So you're saying that atoms like what we have here in our own bodies, they didn't come out of the Big Bang. They're not primordial.
No.
They're not fundamental enough for you.
Well,
Well, all right. You mentioned the sun, so let me say stars. There are a lot of stars in the universe.
that's right. But stars aren't basic enough either, because stars aren't formed in isolation. They tend to form within larger structures that form first, that form before the stars form.
Ah, I'm beginning to see the point. The point is that galaxies are the first large structures to form in the history of the universe. Is that what you had in mind?
That's exactly right. And so I would like to think they are very basic structures, so it's important to study their birth and evolution.
So part of the story we're going to tell today is actually our own story.
Right.
How we got here. And your point is that galaxies were the first major milestone in making ourselves. Is that it?
That's a very nice way to put it.
Okay. Well, let's move forward then and talk a little bit more about the title. We got to galaxies, their birth and evolution. What did you mean by time machines?
Well, you're sort of putting me on the spot here. I sort of made up this title on the spot. So time machines are really telescopes, because we're going to use telescopes to look back in time. We can look out into the distant universe, we can look back in time, we can look into our universe's past. So when I said time machines, I really meant large telescopes.
Ah, okay. Well, I guess that'll become clearer as we go along. The next point is cannibalism.
Cannibalism. Yeah. Well, people get bigger by eating food. Galaxies get bigger by eating other galaxies, and I can't think of a better word than cannibalism, because eating one's own kind is what cannibalism is. And that's an important process in how galaxies come to be the way they are. And we'll talk about this a little bit more.
Okay, and we're actually going to show some nice pictures of that. And finally, chemical pollution, that boon of civilization. Is that what you had in mind?
No, not exactly. This is more in the galactic context, because when we talk about the chemicals that we see in the sun, very often the chemicals we see in the sun and in stars are not produced in those stars. They're produced in previous generations of stars. So when we look at the chemicals in a star, we're often seeing the stuff that was rained down on that star from earlier generations, all the good stuff that was left for it by earlier generations of stars. So by looking at the chemicals, we can say something about the generational age of a star. And we'll talk some more about this too later.
Oh, so those carbon atoms I was talking about before, is that the chemical pollution you had in mind?
Well, some of those carbon atoms are indeed produced in
other stars.
Other stars before the sun.
So human life is a product of interstellar sewage.
That's right. Or stardust.
Stardust.
Put it more elegantly.
Putting it a little bit more elegantly, yes. Okay. Well, with all of that as a bit of introduction, let's get to the heart of our topic, galaxies, and try to clarify exactly what galaxies are like. We brought some slides for this. Our first slide is a slide of a neighboring galaxy not far from us, and it happens to be one of your favorites, doesn't it, Raja?
That's right. It brings a lump in my throat every time I see it.
This is the so-called Andromeda galaxy. It's about 2 million light years from us, meaning that it takes light about 2 million years to travel from us to it. And this galaxy and ours, the Milky Way, are the linchpins, the kingpins of a little group of galaxies, a nondescript, kind of anonymous group of galaxies in the universe that we affectionately call the local group, because it's our local swimming hole. And each one of these big galaxies has some satellite companions. You can see 2 companions of Andromeda in this picture, right here. And they are in orbit around the big galaxy. I'd just like to point out that the sprinkling of stars across the picture here, they are all in the foreground. They're in our own galaxy and they're much closer to us. But that makes the point that Andromeda itself is a vast city of stars.
How many stars in that city?
Well, Andromeda is a pretty big galaxy and it would have about 100 billion stars in it. So that question arises, how come we aren't seeing 100 billion little points of light in this picture? And that's because, especially in the center of the galaxy, the stars are so close together that they seem to blend together. They mush together because our telescopes aren't infinitely sharp. So if we focus in on the very center of the galaxy, it looks a little grainy, and you begin to get some sense of the fact that actually what you're looking at there is billions and billions of stars in that little area. This is another galaxy in the local group which has a lot of very bright, individually bright stars that are very visible in this picture. And in fact, this whole thing brings up the more general point, or the more interesting point, that our own Milky Way galaxy, we are a citizen of the Milky Way. And if you take a picture towards the center of the Milky Way, you can see that the center of the Milky Way is just literally a forest of stars.
Now, Sandy, our galaxy would look like the Andromeda galaxy if we were able to step out of it, is that right?
Yeah, let's make use of this picture that you brought. By the way, Raja took this picture, and it's not just one picture, it's a montage of how many hundreds of individual small exposures which you've put together? Andromeda is actually huge on the sky. It's much bigger than the moon. The moon on this picture would look sort of like this. You can't see it with your naked eye, though, because it's very low surface brightness. At best, on a good night, you can see the very center of the galaxy, but it looks almost star-like because you can see only a small portion. So if we were looking at Andromeda and using it as a model of the Milky Way, the solar system would be out here, roughly, orbiting in a circular orbit around the center of the galaxy. And the picture that we're looking at here is taken from our vantage point looking inward to this dense cloud of stars at the center that we call the bulge. Okay, now, it turns out that most galaxies nearby form a sequence. They can be classified, named after a famous astronomer called Hubble, called the Hubble sequence. And let's walk very quickly through the examples of the Hubble sequence. This is one end. You see a rather spherical object here. Remember from the pictures that we just saw, imagine that this thing has 100 billion stars in it, so that if we could fly really close to it, we'd see them all individually. But standing back at a distance, we only see kind of a star mush. Okay? And this guy is surrounded by individual star clusters, these little bright objects in the periphery, each one of it which is in an orbit around the center. It has some companion satellite galaxies that are also in orbit around it. So this kind of object that is rather spherical, sometimes they're elongated, they're called elliptical galaxies. And now if we walk down the sequence, we now introduce a new element. This object, affectionately called by some astronomers the sombrero, for obvious reasons. The sombrero galaxy has an elliptical galaxy in its middle, but now it has also, in addition to that, a disk of stars. And these disks are flattened, rotating structures. We see this disk almost edge on here. But if you could fly up to the top of the galaxy and look down from here, you would see that the disk is circular in shape.
And the disk is sort of like a spinning frisbee?
Spinning frisbee. That's a very, very good example. That's right. And now as we walk through the Hubble sequence, the elliptical part of the galaxy is getting smaller and less significant, and the disk is getting more and more significant. And in many of these disks, there's a disturbance called spiral arms. But the basic disk is more or less circularly symmetric, and the stars are going around in pretty much perfect circles, all in unison, very orderly. Now we're almost at the end of the Hubble sequence. The elliptical galaxy part has shrunk to practically nothing, and we have a beautiful disk here with beautiful spiral arms. And we're seeing this one almost face on, but sometimes we see them edge on, and the next picture emphasizes how flat these disks are. Here's a mini elliptical at the center, and here's a disk now seen edge on. Every star and gas cloud in it in a circular orbit.
Sandy, does a disk like this stay forever? Are they fragile, or are they really like our ultimate frisbees that don't break?
Don't break until dogs catch them or something like that. Yes, is there a question back there? Mm-hmm. The actual size of this object from here to here is about 100,000 light years. A light year is about 6 trillion miles. But if you multiply 100,000 by 6 trillion, you've got a number in miles that's so big that nobody can really understand that. So we always talk in light years.
You were asking about the thickness of the frisbee or the diameter of the frisbee?
Okay, so in this direction, it's maybe 1,000 light years thick or less. Right. Not that thick. Yeah. Absolutely. That was a very, very observant comment of you. As the elliptical part gets smaller, the morphology and structure of the spiral arms changes systematically, so that the arms are very tightly wrapped at the beginning of the Hubble sequence, and they get looser and more open towards the end.
I wanted to interject a quick comment, Sandy. The
Hubble
sequence that you were talking about, Hubble originally put them together thinking it was a time sequence, so he had that notion in the back of his head. We don't necessarily think it's a time sequence, right?
No, we don't think it's a time sequence at all. And by the end of our talk, I think people will understand better what kind of sequence it is. Okay? But that brings us to our next point, Raja. You asked whether or not these disks were stable structures or fragile. The answer is they're stable as long as nothing else comes by and wrecks them. What else could come by and wreck them?
Maybe another galaxy.
Another galaxy. Another galaxy has a lot of mass. All of that mass is pulling, and so when that mass comes close to this guy, the stars that are busy orbiting in nice circles in this object can get pulled off in another direction, and their orbits can get mushed up and scrambled. And actually, that's probably the most important single idea in our talk, that galaxies can run into one another and wreck each other in the process. We've seen sewage, now we see intergalactic wreckage. So let's look at some pictures of that. We're going to show you a sequence of 3 pictures showing galaxies in the act of colliding. This is at the beginning of a collision when you still have 2 rather distinct objects. One of them is a spiral, like the one we've been talking about, a flattened rotating disk, and another galaxy is coming by and pulling out material into it. And this causes a sort of characteristic S-shaped distortion. It's actually kind of paradoxical. You get an arm or a tail going off on one side, and an arm or a tail going off in the direction of the disruptor.
This is a laterally inverted S, but of course the S could happen forwards or backwards. The other thing I wanted to point out looking at this picture is from the perspective of a big galaxy, it might look like a merger or a nice friendly merger between 2 galaxies, but certainly from the perspective of the smaller galaxy, this is nothing but galaxy cannibalism. It's surely going to be eaten by the big galaxy come a few billion years.
It's going to disappear, isn't it? Right. We had a question down here in the front row. Yeah. So the question is, can you get binary galaxies? Well, before these merge, one is in orbit about the other, and so they are binary galaxies. That's exactly right. And our own Milky Way is not even a binary, it's a triple, because it has 2 companions called the Magellanic Clouds, and they are each going in orbit about the center of our galaxy.
Just follow up on that for a second. Because galaxy orbits are often small compared to the sizes of the galaxy themselves, these orbits don't survive for very long. Soon the galaxies start getting distorted and they no longer are in this nice stable orbit. Right. And that's exactly what's happening here.
This is the next slide in this series, which shows 2 galaxies that were formerly separate entities. Now they've come closer together. They're partway through their merger scenario. Okay, and finally this last picture shows 2 galaxies that have almost completed their merger scenario. And if you just took a picture here, you'd see there was only one object. It's a rather strange looking galaxy, but there's only one galaxy left because the 2 have come completely together. Now, the next and final picture is our first space telescope picture. We're going to tell you more about Space Telescope in a minute, but the whole point of Space Telescope, it's above the atmosphere, it's above the blurring by the atmosphere, and it takes sharper images. And astronomers love to get sharper pictures of things. It's like bringing them closer. You can study more detail. There we go. This is one of the best pictures taken with Space Telescope. It's a pair of galaxies that are partway through their merging. Here's a ground-based picture. You can see clearly the remnants of two disk-like galaxies and two long tidal tails of stars that have been thrown out by this gravitational interaction. And the Space Telescope picture is in this little area here, just to the center, and here it is over here. Here's the center of one object, the center of the second object. And one of the messages in this picture that really caught astronomers by surprise is all of these blue stars that are evident in the picture. Whenever astronomers see blue stars, they know that they're looking at stars that have just formed very recently. Blue stars are very short-lived. They're very massive and they shine very brightly, but they don't last very long. So this picture tells us that not only do galaxies wreck one another in the process of merging, they also often undergo a burst of new stars. So this combination of wreckage plus new stars formed in the collision completely transforms their appearance.
Sandy, you showed us a sequence of 3 galaxies just before this one. You suggested that it's like a time sequence, that one pair of galaxies might later become like the second pair and then finally become like the third pair, where you don't see the two entities anymore. How can we be sure that these 3 different pairs of galaxies are going to go through each other's stages?
So you're saying this is a nice argument, it's kind of plausible that when we show pictures like this, it's really a time sequence. But if these collisions are really occurring, it would take over 1 billion years for one to happen. And we can't sit around here and actually watch changes. So there's an element of guesswork going on when we try to paste these together and make a time sequence out of them, right?
Right. And so there's a second approach one can take in all of this, of course, and that is to try and compress time. And you can do that on a computer. If instead of taking real galaxies and watching them collide, if I built simulated mock galaxies on my computer, I could compress time and I could make 5 billion years into 5 minutes, and I can watch what happens when those two fake galaxies collide. And I'm going to show a little video segment.
Why don't you tell us about this video that we're going to see?
Sure. So what's done in this video, if you second, you'll see that 2 galaxies are going to come together in this video. And before the 2 galaxies come together, you can see they look pretty realistic. The 2 galaxies look like spiral galaxies. You can see them disks, spiral arms. You can even see the bulge at the center. Both galaxies are rotating the way real galaxies do. But they're not 2 galaxies in isolation. They're 2 galaxies coming together. And on the computer, what's been done is every point that you see here is modeled as a point of mass that attracts every other point of mass. So the computer keeps track of how these forces transform the shapes of galaxies. And you see this same S pattern. Do you see this S right here getting disrupted now? So you can see these 2 galaxies, the same 2 galaxies, you can see them go through the various stages of their interaction and merger. Something that you had to imagine for the real galaxy, for the world of real galaxies. So it's nice to have both. It's nice to have the real galaxies, of course, but it's also nice to see that our computer simulations can mimic nature quite well.
Yes, I guess people have taken individual galaxies which they suspected to be collisions, and they've tried to set up in the computer exactly the interaction that would result in the pattern and shapes of these galaxies that we see today. This is a pretty famous segment of film, isn't it? Why don't you tell us a little bit about it?
I guess this is from the National Air and Space Museum. Is that right, Sandy?
That's right. They have an IMAX theater, and they commission IMAX films to be shown there and in other IMAX theaters. And this particular segment, which looks much better on an IMAX screen than we're seeing it here, was computed by one of our astronomers, Lars Hernquist, who's an expert in modeling these galaxy collisions in the computer. And then artists took it and dressed it up and when you actually look at it on the real screen, it's incredibly beautiful. Yeah. Okay, so that's how we know that these collisions are occurring. Oh, we have some questions. Yes, sir.
Okay, with the belief that primordial black holes are at the center of galaxies, how would that theory of two galaxies colliding hold up?
Okay, so the question is, if there's a black hole at the center of a galaxy, or both galaxies, would that really influence the picture of this collision? The answer is not really, not in the large, because these black holes have much, much less than even 1% of the total mass of the galaxy. Now, in detail, though, an interesting situation is set up because you have two super heavy things that each one of them might be 1 billion times heavier than a single star. So you have, in the process of this collision, two very, very massive particles that are careering through the galaxy and creating a lot of havoc with their gravitational field. So in detail, your question is really good, because as these black holes spiral down and get closer to the center of the galaxy where they will ultimately merge, they really wreck the middles of galaxies. And we can see evidence of that when we take pictures of them.
They're sort of like cosmic egg beaters.
Ah, yes, that's a good analogy. Right. As
up.
they whip around one another like this, any little poor star that comes close gets flung out, just the way the cream comes out all over your kitchen wall when you're beating something with your egg beater. Yes? Your question is, did you see on the film that the galaxies were appearing to get smaller as they merged? Is that your question? Raja, why don't you address that?
That's a very good question. In fact, what happens is some sort of redistribution. The part that was difficult to see in that video is the outer parts of the galaxies, the things that were originally in the outer parts of the galaxies, actually get flung out beyond the frame of that picture. So much so that they no longer belong to either galaxy or to the merged pair. So in fact, what's left behind, the part that does merge together, is often more tightly bound and more compact than either of the original galaxies. So there is some redistribution going on. On the whole, some part of the galaxy might get thrown out, but the remaining part of it may be more compact than the original galaxy.
There was some questions way in the back. Could our galaxy crash into another one? Or get sucked in, yes. Are you going to tell us about this?
Not a lot in later, but in fact, the galaxy our galaxy is going to collide with is right there. We have a portrait of the criminal right there. We are going to collide with this galaxy. There's no point holding our breath. It's going to take a few billion years. And the results are going to be pretty devastating, because our galaxy is about as big as the Andromeda Galaxy, and we've seen when two big galaxies come together that are about the same size, they tend to really destroy each other's structure. It's not the case of one little galaxy colliding with a big one. If we were the big one in that case, I'd say not much will happen to us.
Raja, how do we know we're going to collide with this galaxy?
Well, there's one pretty direct way. We can measure the velocity of Andromeda, and it's actually screaming towards us at 300 kilometers per second.
How do we do that?
We'll talk a little bit about this later, but we can do this by taking a detailed spectrum of a star. By splitting the light of a star, or light of the collection of stars, into the colors of the rainbow, we can say a lot about how fast this galaxy or the stars within the galaxy are moving.
Okay.
Talk a little bit about that.
So this is a speeding bullet coming towards us, and in only 10 billion years or so it's going to hit. What will happen to the Earth then, if we were still around?
Well, the Earth would certainly see a brighter sky around us, but there's a very small chance that the Earth would actually run into another star, or that our sun will run into another star. Because when galaxies collide, they pretty much go through each other. Their overall form changes, but it's very rare for stars to collide with other stars.
In fact, in a typical collision of galaxies, there's only one star that hits another star.
Someone likened it to two snails roaming around in the continental US. What are their chances of meeting? It's not very high.
Okay. Where are we going next?
Okay, so we were going to now talk a little bit about time machines and looking back in time. And can I tell a brief little story about how information is backdated?
Sure.
Very quick. So I want to give a little analogy about how we look back in time. Now, I know several of you have come here for this lecture, and you got here at 9 a.m. If you came here from Gilroy, how long do you think it would have taken to drive to Santa Cruz? About an hour? Okay, about an hour. So if I asked you about what's going on in your hometown, the information you gave me would be backdated by 1 hour. if you came here at 9 o'clock, you could tell me what's happening in Gilroy at 8 a.m., but not after that. If you came here all the way from San Francisco, it might have taken you 2 hours to drive, in which case your information would be backdated by 2 hours. If we were so lucky that you came, if you drove here all the way from LA, your information would be backdated by 5 hours. If you drove here all the way from New York, your information would be backdated by 40 hours.
Right.
So the idea is information is backdated. Whenever light comes to us, it carries information, and depending on how far light has traveled to get to us, we are always looking into the past. And how far into the past depends on how far we're looking out into space.
So when I said earlier that this galaxy, Andromeda, is 2 million light years away, what I meant was that this is a picture that looks back 2 million years in time. It shows Andromeda as it was 2 million years ago. We don't really know what Andromeda looks like at this moment. Andromeda conceivably could have gone out or ceased to exist, and we wouldn't know that for another 2 million years or so. Now, what we're going to talk about next is using large telescopes to look out even farther in space and therefore even farther back in time. And this will give us a picture, we hope, of what the universe looked like billions of years ago. And so we actually will be able to see infant galaxies or adolescent galaxies in their earlier state of evolution. So let's take a look at that, okay? All right? So we go out, we spend millions of dollars, we build a big telescope on the ground, we take the deepest possible picture. This one took several nights of exposure time with a ground-based telescope, and this is what we get. There we go, okay? This is a small fraction of the moon, tiny fraction of the moon, 1/10 or 1/20 of the sky, the size of the moon. And it's a typical region of the sky. There are almost no stars in this picture. Everybody here looks like a star, but actually all these blobs that you see here are very faint galaxies that are very far away, billions and billions of light years away.
And do you mean these tiny blobs are physically as big as the Milky Way galaxy, some of them?
That's right. In general, they're just as big as the Milky Way, or almost anyway. It's nice to see them there. The whole celestial sphere has as many galaxies on it at this level as we have stars in our galaxy. We can see 100 billion galaxies over the whole sky if we could picture the whole sky like this. But it's a little disappointing, isn't it, Raja?
Yeah, all we see are blobs.
Yeah, it's hard to learn about any of these things. You can't see their structure, you can't see their Hubble types, you don't even know if they have Hubble types. Can't really tell if they're merging or whatever they're doing. So what are we going to do here? We're going to put a telescope above the atmosphere, and this brings us to the Hubble Space Telescope. Here's a picture of the Hubble Space Telescope as it was let loose from the shuttle, and the shuttle is now pulling away. And we can see what a satellite looks like when it's floating free above the atmosphere. This is not a very big telescope. Its mirror is only about 100 inches in diameter. So like from him to me here, something that's about 100 inches, right? That's not too big as telescopes go. But this one is precious because it has excellent optics and it's above the atmosphere and takes these wonderfully sharp pictures. So now let's retake that picture that we just saw from the ground. It's a different region of sky, but statistically it's the same sort of thing. And this is the deepest, most incredible picture of the universe that anybody has ever taken so far. This is 2 weeks of Hubble Space Telescope time. And this picture now is a small corner of what you saw before. Each one of these blobs, which looked round and uninteresting in the previous picture, now at higher resolution with Space Telescope, you can really see what's going on.
Sandy, this is a tiny patch of sky. This is a grain of sand held at arm's length.
Absolutely, absolutely. A grain of sand at arm's length. Thanks, that's a great analogy. So you can think of this picture as kind of a core drilling in space and in time. The bigger objects are closer to us. They're in the foreground. And the smaller things are in general a lot farther away. They are billions and billions of light years. The most distant things that you see in this picture are 10, 12, maybe even 13 billion light years away from us. And the whole universe began 14 billion years ago. So if you look out more than 10 billion years or so, you're really looking to events that happened early in the universe, early in galaxy formation. Let's zoom in on this picture. Here's another version. This is enlarging pieces of it. Okay? And in this picture, you can see a normal galaxy, which is in the foreground and pretty close to us in time, probably seen maybe only 2 billion years ago in its history. And this little guy, this blob of 4 here, is a famous thing called the Quad. It's actually a galaxy that is still in 4 pieces. Galaxies, as we've seen, grow in size by merging and eating others. This one is seen so far back in time that all it was a bunch of little hunks that had not yet coalesced to make its final form. We have a question here. Well, the first thing we have to say honestly about planets in this picture is that we simply don't know. Okay? The only other extrasolar planets that have been discovered are going around stars close to us in our own galaxy. And what we're discovering is that, this is tentative, that planets only form around stars that are fairly recently formed. There are reasons to believe that planets would not have formed around the earliest stars, and I think you'll actually be able to say something about that in just a few minutes. So, to the extent that this picture is looking very far back in time, the stars in these galaxies probably were not able to make planets yet. And planets are a more recent phenomenon that you would see only in galaxies in the foreground.
Sandy, you're alluding to the fact that chemicals are required, some of these fancy chemicals are required for planets to form.
Carbon, iron, silicon are needed to make planets, that's right. And you're going to tell us where they come from in a minute. Yes? Very good question. As you look farther and farther back in time, can you see the actual beginning of the universe? Would you like to tackle that one?
Sure, we get very close to that actually. As you look further and further back, there comes a time when the universe didn't even have its galaxies. The universe was almost a smooth sea. It was a cosmic ocean of matter and radiation. And the remarkable thing about astronomy, not about optical astronomy, but about radio and submillimeter astronomy, is you can look back almost all the way to the Big Bang. There is an epoch, there's a period right after the Big Bang when the universe was like a very hot furnace and there's some radiation that escapes from that period. The universe was only 300,000 years old then. 300,000 is a blink of an eye compared to 14 billion years. So we can look back. That's about the furthest we can look back with our telescopes. Not with these telescopes, but with other telescopes. We can look back to a time when the universe was an absolute infant. And we can see radiation that was left over from the Big Bang. We can't see the Big Bang itself.
This is called the cosmic microwave background radiation. So we can't see back to time t equals 0, but we can see to time t equals 300,000 years out of 14 billion, which is pretty darn good. Okay, we better move on. I'm looking at my watch and seeing that we actually have quite a lot more to say. So you have probably already guessed that astronomers like Raja and myself like these space telescope pictures, this core drilling back in time, because then we can piece together images of galaxies at different epochs and come up with a theory for galaxy formation and evolution. There's a very well-developed theory for this, which predicts that galaxies agglomerate in little pieces. This is an image of galaxies seen about halfway back in time. And in fact, using Hubble Space Telescope images, people have made this nice slide which pieced together galaxies today, when the universe is 14 billion years old, when it was 9 billion years old, 5 and 2. And by studying the morphology and sizes of objects like this at different epochs, we can figure out what the ages or the sizes and manner of mass accretion was that brought the galaxies together.
Sandy, that's a wonderful story. And even looking at galaxies that are 12 billion light years away, I guess that's what these galaxies are. You can even for galaxies this far away, we can see some detail with the Hubble Space Telescope, but we can't see as much detail as we can see in, say, nearby galaxies. So the thing I was going to spend a little bit of time on next is talking about things that are in our relative backyard. Astronomically speaking, the Andromeda Galaxy is in our backyard. And one of the things we can do is we can look through the Andromeda Galaxy, and there are signs in the Andromeda Galaxy, nothing special about this, but there's signs in all nearby galaxies of traumatic events that went through that happened in its life, that have left a mark on it that can be seen in the present day. In the same way that we can look at fossils today and find out how the creatures that produced the fossils lived. We can look at dinosaur bones today, and all that's left of the dinosaur are its bones. We can still figure out how the dinosaur lived, how big it was, what it ate.
Are you saying that a galaxy like the Milky Way or Andromeda might have actually looked at like one of these irregular blobs in the past, and there might be a sign of that
Might
still?
be some sign of that, maybe not this much detail, but there could be signs of what kind of cannibalism events went on. There might be signs of what kind of interactions it's currently going on in the life of this galaxy, and I want to spend a few minutes talking about that. I'm going to switch media. So we're going to use the Andromeda Galaxy and some of its friends, some of its satellite galaxies, some little galaxies that are orbiting the Andromeda Galaxy, as a fossil of this galaxy's past. So we're using the Andromeda Galaxy and its neighbors as a fossil record of how galaxies form and evolve. And really, I'm going to focus on two things. The Andromeda Galaxy and the small galaxies around it are close enough to us, to the Milky Way and to the Sun, that we can see some telltale signs of what happened in their past. And I'll talk a little bit about those signs. And then, even more exciting, we can witness ongoing cannibalism events. The Andromeda Galaxy is actually eating its little friend over there. I guess they're not friends anymore, but they used to be friends. Now, before I tell you how we see these telltale signs, I want to tell you a little bit about what we can learn from light, what we can learn from starlight. You probably recognize this as the colors of a rainbow, and there are dark lines in this particular spectrum, it's called. This is a spectrum, this might be a spectrum of a star. The dark lines contain a lot of information. If we zoom in to a small segment of the spectrum, what we'd see is a plot like this. Now, instead of showing you the colors, I've actually made a little plot, and every dark band that you see in this upper panel here shows up as a little dip here. Now, these dips carry, they look very insignificant, but they carry a lot of information. These dips, these three dips in particular, exactly where they are tell us how fast the star is moving. So Sandy was talking about how fast galaxies rotate. We can directly measure that by looking at the positions of these dips in the spectrum, exactly where in the spectrum they appear. Now, when you find out how fast a star is moving, that indirectly tells you how much gravity it's feeling, because it's moving in response to a gravitational force. And the gravitational force is caused by the mass of the galaxy the star lives in. So indirectly, by taking a spectrum, we can weigh a galaxy. So this is pretty remarkable. Think about this. There's a galaxy 1 billion light years away. We can put it on a weighing machine and tell you how much mass it contains just by analyzing the light of the stars. Pretty remarkable. The next thing we can learn is by looking at how deep these dips are. This particular dip and this particular dip is very deep, cuts deeply into the spectrum. These are dark lines, some of these are faint lines. The depth of the dips tells us what chemical elements are in the atmospheres of these stars. This is also remarkable. You've got a galaxy 1 billion light years away. You can tell what chemicals make up the stars within the galaxy. That's pretty remarkable.
And how much there is.
So
which chemical causes these three dips?
Those three are actually produced by ions of calcium in this particular star. So it tells us how much milk the star drank as a child. No, it actually tells us about, ironically, calcium is not produced within this particular star. So when we see calcium in this star, it tells us about previous generations of stars that are capable of producing calcium that have polluted this star. So that's what we meant by chemical pollution. Chemical pollution, by studying that in the galaxy's context, we can learn a lot about a history of a galaxy. And that's exactly what this slide is trying to show. Just from the study of chemical pollution, we learn that Andromeda's halo of stars, the ball of stars that Sandy was talking about, was actually formed by the cannibalism of many, many small galaxies. What you see in this plot is a graph showing stars that are very rich in chemicals, stars that are sort of like the sun. on the right-hand side, and stars on the left are poor in chemicals. They're very anemic. They're 1,000 times more anemic than the sun. And what you see in Andromeda is it has a mix of all kinds of stars. Stars come in a variety of types. Some are rich in chemicals, some are poor. What this tells us is the halo must have been formed by smushing together many kinds of small galaxies. Some were rich in chemicals, some were poor in chemicals. And we actually have direct evidence of this. If you look at the small galaxies, like that one there, like that one just off the picture, if you look at the small galaxies around Andromeda today, they actually have the right mix of chemical elements within them, such that if we imagine smushing these together, we would actually get something that looks very much like the Andromeda Galaxy. So it's indirect evidence that the Andromeda Galaxy was actually formed together by smushing together its satellites. Now, since the Andromeda Galaxy is cannibalizing its little friends, it doesn't go unharmed. It is also affected by this cannibalism process. Someone over there was asking what attracts what. It turns out that the small galaxies in the process of merging with Andromeda do some damage to Andromeda. If you look hard at this picture, if you look at the first picture of Andromeda, the second picture of Andromeda, it might look like a normal spiral galaxy as it does on that poster. But if you go to a high contrast image, can you begin to see an S shape in this picture? A very subtle S shape. You can see it more clearly there. It's the same galaxy. Andromeda, again, you see an S. It's a very mild S, but remember we said the S shape is sort of a signature that a galaxy has been monkeying around with other galaxies. Okay? Now, one of the other things these great digital images let us do is they let us study the satellites in a great deal of detail. Here is a satellite of Andromeda, and you can barely see it because it's buried in the light of Andromeda. But what we can do with digital pictures is we can peel away the light of Andromeda and really reveal the detailed structure of this satellite. Something you couldn't do before, but now with digital cameras, you can do this very nicely.
I think by looking really closely at that last picture, I saw a bit of an S shape on that satellite.
Yeah, that's right. In fact,
Sort of going like this a little bit. Certainly on this side. Yeah.
if we come up to this poster sometime later, you can really see a bridge of stars connecting this little satellite. A bridge of stars that's being torn away from the small satellite. Okay, so we love to do these computer simulations, and what I'm going to do now is show you a little computer simulation of what happens when Andromeda's gravity acts on a small orbiting galaxy. So that red blob off to the right, that's going to begin to go around in a circle or in an ellipse. This red blob is a small galaxy that's in orbit around Andromeda. You don't see Andromeda itself. Andromeda's gravity is represented in this computer simulation, but you don't see Andromeda itself. The little hand marks the position of Andromeda, but you can see what's happening to the little guy. It's getting thoroughly ripped apart. And without going into the details, what you see over here is a comparison between this computer simulation on the left and one of Andromeda's real galaxies. And there's quite a remarkable similarity in some of these features, which makes us think this little friend over here is indeed getting disrupted by Andromeda. So simulation and reality show a pretty good match to each other.
So just, can I ask a question? Are you saying that this little red blob here, if you let your simulation go for a couple more seconds.
Sure.
Okay, the red blob is the bright part, and we're supposed to identify that, the red blob, with that little object there?
The yellow stuff over there is so faint that it's lost in the glare of Andromeda.
But if we could study really deeply and see all those stars, we'd see big star trails.
That's correct.
Extending out from that object?
Correct. And there's actually some evidence that we see some of these trails in other parts of Andromeda, not just around this particular neighbor. Okay, so I'm going to talk a little bit next about the following depressing fact. With the world's biggest telescope, this 10-meter telescope on Mauna Kea, we have two of them, two biggest telescopes in the world. It takes one night to get detailed information on a single star in Andromeda. So there's only one biggest telescope in the world. There can only be one biggest telescope in the world. There are billions of stars in Andromeda. and I don't have that many nights, and Sandy doesn't have that many nights to sit and look through every star if each star is going to take up one night of observing time. So one of the things that Sandy's done, a remarkable thing, is she's built this camera and spectrograph that can take spectra of 150 stars or galaxies at a given time. I'm sort of minimizing it when I call it a camera or spectrograph because this beast is as big as the distance between Sandy and myself. This is just a camera that sits on a 10-meter telescope, or will sit on a 10-meter telescope in Hawaii.
So this picture, which is not coming out as well as we hoped it would, at least gives you the scale of this spectrograph, which is called BMO, next to a live person.
Yeah, this is not a simulation, this is a real person. This person could walk around inside that camera, that's how big that camera is. Now, the other thing we'd like sharper views of the universe. We'd like sharp images, and Sandy just talked about the fact that we can use the Hubble Space Telescope because it's in orbit above the Earth's atmosphere, so it doesn't see the twinkling of stars, and it can take sharp pictures. But there's actually a new technology called adaptive optics. And what that does is it allows us to sharpen images that are even taken from ground-based telescopes. Even though we're looking through the atmosphere, there is a technique that lets us compensate for the twinkling of stars, for the blurring caused by the Earth's atmosphere. And I'm going to show you a little animation that describes how adaptive optics works. So bear with me as we go through this animation, and I'll stop the animation at a couple of key points to describe some of the features of adaptive optics, and then we have a little demo after that to show you. So this is a cutaway picture of the building that holds a telescope, and now you're seeing the telescope itself. That right there is a telescope structure, the mirror is down there. And what you're going to see is a representation of how light comes down, bounces off the mirror, it's bounced a couple of times, and now it's going into the camera we talked about, camera or spectrograph. Now you're going to see what happens inside the camera or spectrograph. Light ray comes in, bounces off a couple of mirrors, and forms an image on the computer screen of a star. And you see the star image is dancing around because of the twinkling of, that's what we mean by a twinkling of a star. And if I could stop this here for just a second, what you see is instead of waves coming in as flat surfaces, these things look like Pringles potato chips. You can see that the light waves are being distorted by the Earth's atmosphere. That's exactly what causes twinkling of stars. That's what when you look at these little surfaces, they're not perfect flat sheets, they're highly distorted. So the result of that is this twinkling image. Now what we can do is take this information and we can make a mirror dance around in just the right way. So in this case, the mirror is dancing around, and you notice they're coming in as Pringles, but they're coming out flat. And if we carry on, you see what the flat waves, what they do is, instead of a dancing image of a star, you suddenly get a very sharp and steady image of a star. So that's the magic of adaptive optics. So
We've brought our own. We brought our own little adaptive optics demo with us. And there's a message hidden in here, and you would not be able to figure out what it is. It's kind of like the message hidden in blurry star images. And the technique of adaptive optics lets you see what that message actually is. So what did we do here? There's really no mystery going on. There are two pieces of plexiglass, kind of like shower doors, but unlike a normal shower door, you know, when you look through a shower door, you can't see a good image through it. This is one shower door. This is a matching negative shower door. So when you put these two together, the surfaces exactly interleave, and now looking through them, you get a pretty good image of the world. That's what adaptive optics is all about. You can do it with shower doors, pieces of glass, or more commonly with these deforming mirrors, which exactly cancel out the wavefront aberrations. That's what our new Center for Adaptive Optics is exploring. So what the future has to hold is that Space Telescope, good as it was, is about to be eclipsed by a whole new generation of gigantic 30, maybe even 100-meter telescopes on the Earth's surface using adaptive optics to take pictures that are even much, much sharper than what we can get with Space Telescope today. So now, that's the end of our talk. Thank you very much.
Thank you very much, Sandra and Raja. We have time for a couple of questions.
There was a hand in the back here.
So the question is, when stars get flung out in the process of two galaxies colliding, what happens to those stars? Two of those three things happen. Very often they become free-floating stars, or they can form mini galaxies. They can form little condensations that break off from the parent. It's relatively rare for them to become parts of other galaxies unless other galaxies happen to be in the neighborhood. If we're talking about really two galaxies colliding in relative isolation, then it's very often the case that some get flung out and either become separate mini galaxies or just become free-floating stars.
Question here?
So then are you saying that because the clusters would eventually collapse, that
The universe is expanding. The way these objects form, galaxies, clusters of galaxies, they started out as slight overdense regions in the early universe. Their little portions expanded for a while and then fell back together, making a blob, while the universe continued to expand around them. So just because a little piece of the universe fell back together to make a galaxy or a supercluster doesn't necessarily mean that the universe as a whole is going to fall back. And in fact, from our latest information, it suggests that the universe is going to expand forever, which is good news.
Question here?
That's right.
One more, I think maybe just one more?
One more question in the back.
Yeah.
if creation isn't an option in the theory of the Big Bang, where did you get the starting elements to produce planets and galaxies?
Sure.
We think, in a nutshell, that there were only two chemical elements that came out of the Big Bang in any quantity, hydrogen and helium. And everything heavier in the periodic table, heavier than hydrogen and helium, was cooked in a star. With every new generation of stars, some explode, send their chemical elements out as pollutants into the interstellar medium, where they can now be incorporated in the next generation of stars. And when the abundance got high enough, we think we actually started making planets as well as stars.
So where did the stars start from?
Where did the stars form from? All of these structures form because there's a little bit of extra matter in one place, and that extra gravity draws the particles together to make a thing. In the case of stars, stars are forming out of overdense lumps inside galaxies, because the gas in galaxies is not exactly uniform, it's clumpy. And when the density gets high enough, that's where you make a passel of stars.
So unfortunately, we've run out of time, and I'd like to take this opportunity to thank once again our speaker, Sandra Faber.
We would like to thank you all. You are just fantastic, and we hope you have a wonderful stay at UC Santa Cruz.